When people hear the words black hole, many think of something that pulls everything inward like a powerful vacuum. That idea sounds dramatic, but physics describes something different. A black hole forms when a huge amount of mass is packed into a very small region of space. When this happens, gravity in that region becomes extremely strong. The strength grows so large that light cannot move outward. Since light carries signals, anything that crosses a certain boundary around a black hole can no longer send information back to the rest of the universe. That boundary is important. Outside it, objects move in familiar ways. Inside it, every possible path leads inward. A falling object does not feel a sudden shock or force at that boundary. From the outside universe, however, anything that crosses it disappears from view forever. To explain this, gravity must be described differently from everyday experience. Gravity is not just a pull. Mass affects how space and time behave around it. Objects move along paths shaped by that effect. Near ordinary objects, those paths bend only slightly. Near very large masses, the bending becomes extreme. A black hole represents the strongest known case of this effect. Space and time curve so sharply that all forward directions point inward. Light follows these directions as well. Escape is impossible, not because light slows down, but because every allowed path leads deeper inside. This leads to an important result. A black hole does not pull harder than other objects with the same mass when viewed from far away. Objects can orbit it normally. Light can pass nearby and continue outward. The unusual behavior appears only close to the boundary where escape ends. Black holes form through natural events. Very massive stars produce energy that pushes outward for a long time. When that energy supply runs out, gravity takes over. The star collapses inward, growing smaller and denser. Under certain conditions, nothing halts that collapse. The result cannot be seen directly. Its presence is detected through the motion of nearby matter, the bending of light, and energy released by material close to it. Black holes appear simple when described from the outside, using only a few physical values. At the same time, they point toward areas where present physics reaches its limits. That combination keeps them central to modern science. To go further, it helps to describe a black hole in plain physical terms. A black hole is not an object made of a special substance. It does not have a hard surface like a rock or a planet. In physics, it is a region of space where mass has changed the behavior of space and time so strongly that escape becomes impossible beyond a certain boundary. What defines a black hole is not the material at its center. What defines it is how motion works near it. Every object moves through space and time following allowed directions. Under ordinary conditions, many directions are available. You can move away from the massive object if enough energy is used. Near a black hole, the set of allowed directions changes. As distance decreases, fewer directions lead outward. At a specific distance, every allowed direction leads inward. That boundary marks the defining feature of a black hole. Beyond it, moving away is not an option. This applies to everything, including light. Light does not get trapped because gravity pulls harder than usual. Light remains trapped because space and time have been reshaped so that outward motion does not exist. This challenges everyday expectations. In daily life, stronger motion allows escape from stronger gravity. Rockets leave Earth by moving fast enough. Near a black hole, speed does not help. No amount of speed changes the outcome because the structure of space and time determines motion. Another common expectation also fails. A black hole does not pull objects inward from far away like a giant vacuum. From a distance, it behaves the same way any object with the same mass behaves. Stars can orbit it. Gas can circle around it. Objects can pass nearby and continue on their way. The extreme behavior appears only close to the boundary where escape ends. This explains why black holes can exist without destroying everything around them. Many galaxies contain a black hole at their center, while billions of stars move normally for very long periods of time. Time also plays a major role near a black hole. Gravity affects time as well as space. Clocks closer to a massive object run more slowly when compared with clocks farther away. Near Earth, this effect is very small. Near a black hole, it becomes very large. From far away, objects falling toward a black hole appear to slow down as they approach the boundary. Light sent outward becomes weaker and stretched to longer wavelengths. Signals take longer to arrive. From that distant viewpoint, the crossing seems to take an extremely long time. For the falling object, time continues normally. Nothing unusual is felt at the boundary. Motion continues inward without warning. This difference does not come from illusion. It comes from the way time behaves in strong gravity. Both descriptions are correct within physics. Time does not behave the same way everywhere. Inside the boundary, the behavior of space and time changes even more. Directions that once allowed escape now point inward only. Movement toward the center becomes unavoidable, in the same sense that movement toward the future is unavoidable. This comparison helps explain the situation without advanced math. Just as time moves forward rather than backward, motion inside the boundary leads inward rather than outward. This is difficult to match with everyday experience because nothing familiar behaves this way. In daily life, space always offers options. Inside a black hole, those options disappear. Black holes also have size. The boundary does not sit at a single point. Its distance from the center depends on mass. A black hole formed from a star has a boundary only a few kilometers across. A black hole at the center of a galaxy can have a boundary larger than the orbit of planets. This leads to another surprising result. A person crossing the boundary of a very large black hole would not feel immediate effects. The stretching forces that damage objects grow stronger closer to the center. For small black holes, these forces grow quickly. For large ones, they grow more slowly. Black holes also share a simple description. Once formed, they can be described using only a few values: mass, rotation, and electric charge. The detailed history of the material that formed them does not remain visible from the outside. Different stars can collapse and leave black holes that appear identical. This raises deep questions. Physics relies on the idea that information is preserved. Black holes challenge how that idea applies when escape is impossible. These questions remain active areas of research. Despite this, black holes are not speculation. Their effects on nearby stars, gas, and light have been measured. Powerful energy releases around them match predictions with high accuracy. So a black hole is not a hole in space and not a cosmic monster. It is a region where mass reshapes space and time so strongly that escape disappears beyond a boundary. It follows strict physical rules. Its behavior can be predicted, and it shows how gravity, space, and time connect under extreme conditions. That is why black holes hold such an important place in physics. They take familiar ideas and place them where everyday expectations fail, while physical laws continue to apply in precise and testable ways. This description of black holes leads to several results that feel strange at first, mostly because daily experience offers nothing comparable. One important result involves motion near a black hole. Far away, objects move in familiar ways. They can circle around, fall inward, or pass by and continue onward. Near the boundary, motion becomes increasingly restricted. Objects do not suddenly lose control. Instead, the range of allowed motion narrows. Moving outward becomes harder, while inward motion becomes easier. This explains why falling into a black hole does not feel like being dragged. There is no sudden pull. The motion feels natural and smooth, even though the outcome is unavoidable. Gravity does not act like a rope pulling inward. It acts by shaping how motion works. Another result involves light. Light behaves like any other moving thing near a black hole. It does not bounce off a surface or get absorbed by a wall. It simply follows the rules set by space and time. Near the boundary, light sent outward fails to reach distant observers. Its energy decreases as it climbs away from the strong gravity. Signals stretch out and fade. This fading explains why black holes appear dark. They do not block light like a solid object. They simply prevent light from reaching faraway observers. This leads to a practical question. If black holes cannot be seen directly, how are they detected? Their presence is revealed by their influence. Stars orbit around invisible centers. Gas meets up and glows as it circles rapidly. Light bends around empty-looking regions. These effects point to something massive, occupying very little space. Another major result involves time differences. Near a black hole, time passes at different rates depending on location. This is not an illusion or a trick of perception. It is a physical effect measured in many situations, even near Earth. Near black holes, the effect grows large. From far away, clocks near a black hole tick more slowly. Signals take longer to arrive. Light loses energy as it climbs away. These effects combine to make motion near the boundary appear frozen from a distance. For the falling object, none of this feels strange. Time flows normally. The object continues inward without sensing any barrier. This difference in experience exists because time itself behaves differently depending on gravity. This result challenges how events are usually thought about. Two observers can describe the same process in different ways, and both descriptions remain valid. Physics allows this because space and time do not behave the same everywhere. Another surprising result involves size and danger. Small black holes and large black holes behave differently near their centers. For small ones, stretching forces grow quickly and can damage objects early. For large ones, those forces grow slowly. Crossing the boundary of a very large black hole may not cause immediate harm. This means danger does not come from the boundary itself. It comes from how forces change deeper inside. This distinction helps remove a common misunderstanding. The boundary does not act like a crushing wall. It marks a limit on communication, not a place of destruction. Black holes also raise questions about information. Objects falling inward carry structure, motion, and internal detail. From the outside, those details appear to vanish once the boundary is crossed. Physics relies on the idea that information does not disappear. Black holes force careful thinking about how this principle applies. Current research suggests that information is not destroyed, but the exact way it remains encoded is still being studied. This question connects gravity, space, time, and quantum behavior. It is one of the most active areas in modern physics. Despite these open questions, much about black holes is well tested. The motion of stars near invisible centers matches predictions. Energy released by glowing gas follows expected limits. Light bending agrees with calculation. Even ripples in space caused by black hole collisions have been measured. These observations confirm that black holes behave exactly as the theory predicts, even under extreme conditions. Another important result concerns simplicity. Once formed, black holes lose almost all visible detail. Their outward behavior depends only on mass, spin, and electric charge. Everything else disappears from view. This makes black holes simpler than the stars that formed them. This simplicity hides complexity. The material that formed the black hole had structure, motion, and history. That information no longer appears in the outward behavior. This contrast between simple appearance and complex origin continues to challenge physical thinking. Black holes also connect directly to energy limits. There is a maximum amount of energy that can be released by material falling inward. That limit matches observations of powerful cosmic events. Black holes act as natural engines, converting motion into radiation with high efficiency. This explains why black holes are linked to bright sources seen across the universe. They do not shine themselves. Matter near them does. Another result concerns growth. Black holes can gain mass by absorbing nearby matter or by merging with other black holes. When two black holes combine, the result is a larger black hole with new properties. These events release energy in the form of space ripples that spread outward. These ripples carry information about the motion and size of the black holes involved. Measuring them allows direct tests of gravity under extreme conditions. All of these results point to a broader meaning. Black holes show that gravity is not simply a force pulling objects together. It shapes how space and time behave. It controls which motions are allowed and which are forbidden. Under extreme conditions, those rules lead to outcomes that feel strange, but follow strict logic. Black holes do not break physics. They reveal how physics operates when pushed to its limits. They also show that everyday experience reflects only a small range of possible behavior. The universe allows forms of motion, time behavior, and structure far beyond what is familiar. And yet, even in these extreme cases, the same physical rules apply. They do not fail. They simply lead to results that feel unfamiliar. That realization sets the stage for bringing everything together into a single picture of what black holes represent in physics and what they reveal about the structure of the universe itself. All of this brings the full picture together in a practical and usable way. A black hole is a region of space where a very large amount of mass has changed space and time so strongly that escape ends past a certain boundary. That boundary defines the black hole. Outside it, gravity behaves in familiar ways. Inside it, motion always leads inward. This behavior comes from how mass shapes space and time, not from a special surface or material. From far away, a black hole behaves like any other object with the same mass. Stars move around it. Gas circles it. Light bends near it. Objects can remain in stable motion for very long periods. Nothing unusual appears at large distances. The extreme behavior shows up only very close to the boundary where escape ends. This explains why black holes do not destroy everything around them. They do not pull objects inward from across space. They affect nearby matter in the same way other massive objects do, until something moves very close. Many galaxies contain black holes at their centers, while billions of stars continue moving normally. Physics has strong confidence in many parts of this picture. The motion of stars near invisible centers follows predicted behavior. Gas near black holes heats up and releases energy in measured amounts. Light bending near them matches calculation. Space ripples produced when black holes combine have been detected directly. These observations confirm that black holes behave exactly as theory predicts, even under extreme conditions. Physics also describes size and growth with high accuracy. The boundary size depends only on mass. Black holes grow by taking in matter or by combining with other black holes. Energy released by nearby matter follows strict limits that match observation. These are measured facts used every day in research. At the same time, Physics does not claim answers to every question. What happens deep inside the boundary remains uncertain. Current theories describe motion inward, but the conditions there exceed what existing models can fully handle. Gravity under those conditions is still being studied. This is an area where new theories are being tested and refined. Information raises another open issue. Objects falling inward carry detail, structure, and internal motion. From the outside, that detail disappears from view after crossing the boundary. Physics relies on information being preserved, yet black holes challenge how that rule applies when escape ends. Research suggests information remains encoded in subtle ways near the boundary, but a complete explanation is still under development. These limits do not reduce what physics explains well. They mark where current knowledge ends and where active research continues. The broader view that emerges remains practical and grounded. Black holes show that gravity does more than pull objects together. It shapes space and time. It decides which motions remain possible and which do not. When mass becomes extreme, these rules lead to results far removed from daily experience while remaining consistent and reliable. They also show that extreme behavior does not require new physical laws.